Roll music, any old way you choose it. It's got a backbeat, you can't lose it. Any old time you need it. It's gotta be rock and roll music if you want to dance with me. The second verse I like. Way down south, they gave a jubilee. And country folks, they had a jamboree. Drinking homebrew from a wooden cup. The folks dancing got all shook up and started playing that rock and roll music. Any old way you choose it. It's got a backbeat, you can't lose it. Any old time you use it. It's got to be rock and roll music. If you want to dance with me, I say, if you want to dance with me. I normally do this, Professor Hanson, so that people will settle down, stop telling doubtful stories to each other, and get ready for the talk. A talk about geology needs a song about rock, so you heard one. We also have refreshments, and I'm sure you noticed, were baked by many of our friends here, including rock-like things like geode cupcakes, conglomerate cupcakes, and wait for it, choco lava. Welcome to the 29th TSVA event. TSVA event, the first of our new season. We hope to have 5 or 6 events between now and May. In November, we'll hear about the movies from someone who lives in the village who writes them. In January, we'll hear a village resident present songs by great composers like Mozart and Schubert. In March, you'll hear old-time radio programs from the 1930s and 40s presented by some of your friends here in the village as a staged reading. You will enjoy that because you will hear the programs. With your imagination, you will see what happens. And meanwhile, you'll see the actors sitting in the studio in sweats, reading the scripts. If you forgot to join the Shoreham Village Association today, it's not too late. You can join today. As you know, there are forms out here you can fill out if you'd like to send in and join. You don't have to pay any dues. We welcome contributions. If you'd like to make a donation, we suggest something like $25 for each family. There are about 60 families in Shoreham that belong to this, so quite a few of us belong, and you might as well join too. There's no downside. I want to thank David Madison for suggesting this topic, which we think is a good one for this series, and finding the speaker. Distinguished Service Professor Gilbert N. Hansen of the Department of Geosciences at Stony Brook University, the State University of Stony Brook, the State University of New York at Stony Brook. Let's get it right. Professor Hansen will tell us about the birth of Long Island, which is just an infant in geological time. It's only 20 or 30 millennia old. I think time goes back 4 billion years to the Earth. The planet goes 4 or 5 billion. It's quite a while. So it's an infant, but that's okay. Young is good. You might be surprised to hear how much the climate and the sea level have changed in that short time. I think you'll hear about it a little later. If you aren't here today, by the way, to hear this talk, some of you aren't here. Some of you aren't here in one way or another. It's no problem because tomorrow or the next day you'll be able to see it on the video. We'll record it. It's being recorded even now. And it'll be on our local website, shorehamtsva.org. Easy to remember. It's no problem to do that. It's going to be no problem at all to hear the talk today. It is indeed my pleasure to present climatic history and geology of Long Island, Professor Gilbert N. Hansen.
I'm testing. Can you hear this? Yes. Okay, good. Thank you very much. It's a pleasure to be here. And I'm going to be presenting some ideas that I hope are new to some of you. And some of them are revolutionary, even though they're almost 150 years maximum were 20 to 25,000 years ago created Long Island. If it weren't for the glaciers, there would be no Long Island. And that's another thing we're going to show here. Most of the surface features on Long Island were created between 25K kiloyears and today. And most of them actually were formed between 25 and 10,000 years ago, 11,000 years ago. And it consists of moraines called push moraines. The two major moraines on Long Island, the Ronkonkoma moraine and the Harbor Hill moraine, are not moraines thought of in the way you're taught in school. In school, you're taught that the glaciers come forward, they dump a bunch of till, and then they go back. In the case of Long Island, because of our special circumstance, when the glaciers advanced, they pushed this underlying sediments, and that's why they're called then push moraines. So the moraines are pushed up. And then we'll talk about tunnel valleys. Has anybody ever been in a tunnel valley? You couldn't get here without going in a tunnel valley. Right out there. When you come in what is the name of the road?
Woodville Run.
Yeah. That's in a tunnel valley. We'll talk a little bit more about it. And they're all over the North Shore. And we'll talk about how they formed. And we'll also show how kettle holes form. Because most people have a misconception about how kettle holes form. Maybe most of you don't, but some of you do. And we'll tell about it. And then we'll talk about a period called the Younger Dryas, which happened about 12,900 to 11,500 years ago, when after it had been warming up, it became very, very cold. And this is a climatic event that some people are very concerned about because associated with global warming, there's also the possibility that as we get warmer and warmer, we could flip a switch and then we become very, very cold. We don't know exactly why the Younger Dryas formed, but we're concerned about it. We'll talk about what it was like, but not give you the answers because we don't have an answer. So the climate has changed from desert tundra to temperate forest. And so 20,000 years ago, this was a desert tundra. And we'll talk a little bit about that later. So this is a DEM of Long Island. And a DEM is a digital elevation model. And what you can do is you can just take data from a normal topographic map and assign elevations at any one point, and also assign latitude and longitude. You can put that into a program, a raster of data, assign colors to different elevations, and then after you do that, you can plot the data, and if you did that, you'd have a nice, beautiful color arrangement, but they add something else to it, which is called shaded relief. And if you look at this data, you'll see the sun is shining in this direction because it is shaded, three-dimensional view. Once this data became available, you could see things that you just didn't imagine were there on Long Island. And you can see it's geology, that's Long Island. You can see what you're a geologist, you can see all sorts of features. And of course, the major feature that we're all familiar with is the Ronkonkoma moraine. Oops. Oh, here I went backwards. This is the Ronkonkoma moraine. It forms the South Fork of Long Island, and it comes up to the center. There's this big mess. I don't know how that formed, but there is a big mess there. And then the Harbor Hill moraine is along the North Fork. There's only a little bit left of it because cliff erosion has eliminated most of it. And then I think we are about right here. Is that right? Somewhere here. And then here's the Harbor Hill moraine. It goes all the way across. So we got these two major moraines, and they are dominantly formed by pushing of the underlying sediments. We'll talk about that. So if it were not for the glaciers, Long Island would not exist. the land under us would still be here, except what would it be like?
In other words, it hadn't been made high enough.
To get above there, and we'll show that now. Here is a cross-section of Long Island. This is the Long Island Sound off here. Here's the Atlantic Ocean over here. This just shows all of the different kinds of materials that are below us. Loess-Lloyd sand, Raritan clay, Magathy. These are our Cretaceous sediments. And what's called Upper Pleistocene here are glacial sediments. And yes?
I don't know exactly what moraine is.
A moraine is just a place where you have a pile of debris that was built in front of the glacier at some point.
It's dedicated word for that exact meaning, I think.
Yes. And it's just a place where the glacier has produced a ridge of sediment. And we'll go into how these were formed. But thank you for asking. It's important if I say something that doesn't make sense, that you ask questions about it, because it's easy for a geologist to say a word and then and not assume everybody knows it. Okay, and then so let's take a look. Here's sea level, and here you can't see sea level over there. Let's just put a line across sea level. You can see everything above sea level here is pretty much glacial. Is that right? The Pleistocene stuff is all glacial. Mm-hmm. So if it weren't for the glaciers, we would be floating in a boat.
Pleistocene is a certain era.
Pleistocene is from 2 billion years till now. And it's the time of continental glaciation. We've had continental glaciation in North America for 2 million years, a little over 2 million years. And that's something also important. We're not at the end of the glacial period. We're not even probably in the middle. We're probably in the beginning, because it's expected that glaciation will continue far into the future, where the continental glaciers come forward, go back, come forward, go back, come forward, go back.
Would it be too much trouble, too much distraction, digression for you to explain to us why it happens?
Well, the reason it happens, you can correlate the advances and retreats of the glacier to the amount of sunlight that hits at 65 degrees north. And that's associated with the ellipticity of the Earth, rotation around the sun. It's associated with the dip of the Earth's axis, and it's associated then with the wobble of the Earth's axis. All those things together, you can make calculations as to how much light was shining there, and it seems that exactly how much light shines at 65 north, which is mostly in the Atlantic that's controlling it, that it turns off and turns on the glaciation.
And wobble has a 26,000 year period.
Yeah, that's 22. Yeah.
22.
Yeah. Okay.
That gives you a feel.
Right.
Every 10,000 years or so, you look at the
Well, the bigger one is every 100,000, and then the other ones are there's just complete changes when they all come together. All right. And so now this is a picture of North America at the last interglacial period. There have been a number of glacial advances and retreats, probably about 20 so far, and they're going to continue many more in the future. And this is a picture at the last interglacial period, and this is at 130,000 years ago. And you can see now, here's St. Lawrence River. There's no Long Island. Can you see that? That's where Long Island would be. And for two reasons. One, the land surface here was not high enough because the glaciers had left material here, but also the sea level at that time was 28 feet higher than it is today. It was also warmer.
not much before either.
No, nothing. So now, this is what the glaciers look like about 35,000 years ago. And Long Island is going to be there. Not Long Island, the place where Long Island is. You can see it's not inland. That's because the sea level is low. And so the Long Island is actually going to be just part of the continent. It's not a Long Island. So the material that's below was there. And you can also see then that the glacier, this is St. Lawrence River through here. If you're familiar, that's going to be Superior, Michigan, the other lakes. So here's the St. Lawrence. So it's a little bit south of St. Lawrence. It's got a ways to go. And it starts heading south. The front of the glacier just starts heading south. And eventually it gets here at around 25,000 years ago. And it's traveling at the rate of 100 yards a year. See, for geologists, that's unbelievably fast. 100 yards a year, yes?
So you say in 100 years from now, will we be underwater or not?
100 years from now will probably be, sea level probably maybe 4 or 5 feet higher than it is now. So it won't be that bad. I worry about thousands of years from now. But for most of us, even 100 years is beyond our lifetime. Okay, so now this is the glacial at the maximum. If we go back, you can see the glaciers were covering pretty much everything, but the center here wasn't covered. Now it's coming way down, and here we can see is the land that was desert tundra. We'll come back to it. And so at this period there's a desert tundra, and Long Island is right there. You can see when the glacier hit us, we were not near the ocean. The ocean was about 70 miles to the southeast, so it would be 70 miles about from there to there, and that's where the glacier is at that time. So this just gives you a view of what things look like. So what glacial features are found on Long Island? I'm going to not give you all of them. I'll just give you some of them that you should be able to recognize yourselves now as you go around. Oh, yeah. Oops. One of them are the bush moraines. We're going to be looking at them. And on Long Island, moraines are not made of just till. And we'll have to show you what till looks like. Till is a mixture of sediments of different grain sizes that form at the base of the glacier of a continental ice sheet. And it's made up of silt, sand, pebbles, cobbles, and boulders. And it's usually about this thick, about 3 foot thick. And it's formed as the glacier travels across the surface. And if you're familiar with faults, it's essentially one big fault zone. And it's pretty much consistently about 3 feet thick everywhere you find it, except now if you get irregularities, and it can either be thinner or thicker depending on the shape of irregularity under the glacier. So they typically consist, and on Long Island, they don't consist of till. Well, they do have till in it, but they're not. That till is not the major material. They consist of silt, sand, and gravel that are usually sorted sediments. They're sediments that were laid down in water, mostly in streams, but some in lakes. And Cretaceous sediments. Remember the Cretaceous sediments at the bottom of this cross section? They are also enclosed in the moraines. And the reason they're there is they've been pushed up from well below the surface, pushed up to the surface by the process. So let's take a look at the common materials that form. This is the glacier outwash. Here would be a glacier. You can see the till would be forming under the glacier. And then as water comes out from under the glacier, most of the water on a glacier comes from underneath the glacier, from tunnels and other places under the glacier, comes out and forms streams, and then you get this pattern of streams and sediments that are being formed. There's a lot of water, a lot of of sediment that's coming out of it, and it forms in periods of sands and gravels dominantly forming as river sediments. So, and this is a picture of till. And in this case, there's a lot of cobbles and boulder-sized material. You can see it's going to be a compact mess. You can cut it and it will form a nice cliff face. And you can also see that, figure out why. Let's say the glacier was 2,000 feet thick as it's pushing down on it. I use a terrible analogy, but I ask a person, what would you think happened if you were laying underneath a glacier and it's 2,000 feet thick pushing down on you? And you'd get squished, right? And that's what's happening to these sediments. They're getting squished like mad. And as a result, they are very competent, very compact and competent. And you look along the north shore of Long Island, you're going to see at the top of the cliffs here are till. And we wouldn't have these cliffs, these bluffs, if it weren't for that till. They're what's known as cliff formers. Because if there weren't till there and it was just sand and gravel, you'd just have a pile of sand and gravel, right? And it would erode very rapidly. But here the till is holding the cliff faces up. Yes? Competent just means that it doesn't fall apart easily. Right? It's compressed hard, and so it doesn't just fall apart. If it was incompetent, you put it down and it would just flow. This stuff, it'll just sit up there. In some cases, it's almost like a rock. Okay, so this gives you a picture of what till is. And you can see, because it's under the glacier, it's got rounded cobbles. Because as the glacier is traveling, the boulders and cobbles, they get rolled and they get braided. And so as that process goes on, they get rounded and broken. And they get smaller and smaller as the glacier goes along. And it's a grinding action. So this is a picture of till at Stony Brook University. They did some analysis. Here you can see the outwash glad. These are stream sediments down here. I'm sorry, it's a bit washed out here. But the till is the material right here that's just at the base here. So we got outwash sediments. They're called outwash because that's what happens when the water comes out of a glacier. You just call whatever comes out is washed out. But it's formed in streams, mostly streams. And then you can see this is the till up in here that's sitting on top of it. And quite often, that's all the till we have, is just 3 feet of till sitting on top of the underlying sediments. And here is a picture from Comstock State Park, and we got till at the top. And Comstock State Park, the cliff faces are about 100 feet thick. Yes?
What will happen to New York City in the future?
Sorry, in the...
Sorry?
Repeat the question.
What will happen to New York City in the future?
Well, if sea level continues to rise, the low parts of New York City will suffer more and more damage, similar to what we had during Sandy. And so there's no question the lower areas are going to be underwater. And most major cities in the world are near the oceans, right? And they're all sort of, not all of them, but many of them are in danger of having that happen to them. And so now, this is the till on the left at the top. This is the glacial outwash sand and gravel. You can see there's a lot of it. And you can pick out the Cretaceous sands because they're usually more colorful. The glacial outwash sands and gravels are usually this tan color. And the Cretaceous ones were formed in a tropical environment, so they developed much more range of colors and blacks and reds and oranges. And so you can usually pick it up. There's the Cretaceous. It's a dark, different color completely. And that's what's making up our moraine. This is on the moraine itself right here. So you can see this is what moraine material is like. It's not till. scalar features were formed by pushing by the glaciers, or are positions where the glacier was stagnant. And so it's not as if we have this one ridge that is just made by one process. It's all, the pushing is a key major factor, but the places there was no pushing is also there. And this is a model that's been developed in Netherlands and Germany for how they view it. And so what happens is the glacier comes along, and I don't know how glaciers make the decision, but they decide that about now it's time for me to push the sediments up. And you can see that's what the glacier said right here. It said, I'm going to push those sediments up. And it does. It pushes them up and forms these sheets of underlying sediment material. And this is 3 miles. It's a scale of 3 miles. So it's pushing them up really long distances, pushing them long distances. And you can also see that they're thick, that they're many tens of feet thick. So these are big sheets that are being pushed out. When you're looking at them, for example, in here, that's a sheet of sediment that was pushed out. And that is a sheet of sediment that was pushed out by the glacier. And the boundary between them is just a place where the 2 sheets were pushed relative to each other. And so that's pretty much the view of how these valleys, or these moraines formed on Long Island. And they also then quite often have this kind of form to them, of an arcuous feature on the front. And I like to point, this is what's called, this is on the Harbor Hill Moraine, but this is called the Port Jefferson, or Stony Brook Moraine. And you can see it's got this beautiful arcuate structure, and you can just picture it as being just one of these sheets that are being pushed up. So glacier is not traveling as one mass forward. It's in little streams, essentially streams of ice that are traveling, and they're traveling semi-independent of each other. And so then that's why you get this one. Here's one, and this point here you don't get quite so much pushing, and there's another one coming off there. And this is actually the zone between the two sheets that are there. Yes?
How fast are these ridges forming and moving?
Well, the glaciers tend to move on the order of feet to yards, or 100, up to 100 feet yards a year or something like that. But the thing is, they don't just go forward. They go like this. All the time, they're going back and forth. It's not always clear why they do it, but it's usually thought that during the winter they'll go forward, and in the summer they'll come back. That's the really small ones. And then other times they'll go forward, and then they'll go back many, many miles, and then come forward again.
Scrubbing the landscape.
Scrubbing the landscape, pushing the landscape, doing, yeah. You can't see much of what happened in earlier glacier periods because the glaciers erase most of the earlier features as they do that. So when you want to find out what happened in earlier times, you have to go look at very special places to find out where it was. Because once the glacier goes over, it does a good job of hiding things. Okay, and here's just a picture now. This is Ronkonkoma Moraine, and I just brought a little picture here to show you where the Ronkonkoma Moraine is. When you look at this picture, you can see it's not a continuous moraine. And here's just one little picture of Bald Hill is about here. If you're familiar with the Suffolk Community College, it's in Selden right here. It's its own little tiny moraine right there. Just a little bit. It's separate from this. And then you'll notice there's nothing here, right? If we look closely at it, we can see these are both push moraines. And this one's about the right sort of size for a 3 mile wide push. And here, there was no pushing. The glacier front was about here. And in this case, there was no pushing. And so what's left behind is just sort of debris that was dropped by the glacier. It didn't even make a moraine, process. So that's stagnant ice, and that was live ice. So the ice came here, it just stopped and let out the debris that was associated with it, and then it retreated. Okay, here's a DEM of Long Island, and again here's the Ronkonkoma moraine, and that's the Harbor Hill moraine. So after the Ronkonkoma moraine formed, this is one of the hypotheses at least, the Ronkonkoma moraine formed, then the glacier retreated, and we don't know how far it retreated, but it retreated at least up into this Long Island Sound area at that time, and it formed a big, beautiful lake. And the lake was dammed by Ronkonkoma moraine and by the glacier sitting off in here. And then the glacier re-advanced and formed the Harbor Hill moraine in the same process that we talked about earlier, by the pushing process.
So it's a back and forth process.
Yes, it's very dynamic, yeah, and it's almost, most people want to think about it because they don't have any other basis to it. It just moves forward, stays there, and then goes back, and every 100,000 years it doesn't, it's going back and forth all the time. Okay, and it's not always related to weather, it's also related to inside the glacier. These streams are fighting with each other, trying to get out. So what we've done is we've done some cosmogenic ages of boulders, and they date the duration of the exposure of surface of boulders to cosmic rays. And cosmic rays convert oxygen to beryllium-10, and the amount of beryllium-10 formed is proportional to the exposure time. So you can use the upper surface of a boulder. You can take out, analyze beryllium-10, calculate the age. And here's Jörg Schaefer, who's doing it. He did it on Long Island. And he's sitting on this boulder and taking off a very thin surface piece of it. And it's going to use it for analyzing beryllium-10. And he gets an age of 17,000 plus or minus 2,000 years.
Where is that picture? Yeah.
That's, if you're in Port Jefferson, you go up Main Street, and then if you are going up, then you look on your right, once you pass Reeve, which is down here, then there's this parking lot.
Dr. D. Benedetto is talking.
Yeah.
You know him, okay, good. And you can see, for some reason, they thought they could break the boulder. And you can see that all sorts of places they tried to break it, and they just gave up and built a parking lot around it, or asphalted around it. Okay, so these are the ages that have come up. And when we did it on Ronkonkoma and Harbor Hill, with an uncertainty, 1,000 or 2,000 year uncertainty, they're the same age, about 18,000 years old. That's the period then that they were, how long they've been exposed to cosmic rays. And what's interesting is this goes up into Connecticut, that matches in Connecticut. And then in Cape Cod, you can see that's 19. That's consistent with Ronkonkoma, because that has a 1,000 or 2,000 uncertainty, 1,000 or 2,000 year uncertainty. What's really surprising on Martha Vineyard, they got 23,000 years. If we have the same sort of relationship here that here, as we see here, you can see there's a possibility there was an advance of a glacier at 23,000 that came much further south of Long Island. So I don't like the term terminal moraine because you never know. Terminal moraines, that means yes, it's where they end, but there always could be another one. So just call them moraines, right? Okay, tunnel valleys. Along the North Shore, there are numerous dry and wet valleys that are formed by subglacial streams. And you can see them. All these valleys here are tunnel valleys. And the tunnel valleys, you can see how they form. They get this pattern, which is called anastomosing, because they just go every which direction and cross each other. And all over, pretty much everywhere on North Shore, you're getting these sorts of patterns. And those are tunnel valleys, and there's a big tunnel valley. Those of you who go to Port Jefferson have notice that it's pretty steep, and then when you get to the railroad tracks, it gets smooth, and nice smooth in front of you. Well, it ends up, this is one humongous tunnel valley. And when it came up, you can see that the glacier was sitting right here, and the water came pouring out of that tunnel. The tunnel valley is formed from a tunnel in the ice, and that tunnel has water on it, and it spewed out all these sediments from that water. So you can imagine there was just a tremendous amount of water coming out. And so that's called an alluvial fan, if you like names. And then, so where did the water come from? Well, melting at the base of a glacier by Earth's internal heat. The heat is always coming up from the Earth, and under the glacier gets thick enough that heat can build up, and you can get enough melting of the bottom of the glacier. And of course, there's melting of the surface during the summer. And this is a picture of melting at the base of glacier just from Earth's internal heat. Here's the Antarctic ice sheet. They lifted it up so you can see it. And you can see now all this blue stuff, the light blue stuff are lakes, and the darker blue stuff are streams under the glacier. And that's just melting. This is a surprise that there's that much melting, and you know that there's not much melting on the top of the Antarctic ice sheet, right? It's too cold. So there's a lot of melting that's coming in that sort of process. And then, of course, in Greenland, you can see, this is just one view of it. Here you can see that the melting in the summer is just coming down like mad, and this is going into we call them moulins. They're just a hole in the glacier. Water finds a place to seep down, and then it keeps going down, and it goes down. And so this is the process for forming then tunnel valleys. Here is water going down in the moulin. It's going into a tunnel under the glacier, and then the water comes up. And this is a problem that people have a hard time. Can water come up? And this is a tunnel. And how would you like to be standing in front of that, where that water tunnel is filled with water, and it's spewing out? I know. And so you can picture this here has to be about 18 feet in diameter. Is that right? You can put a truck in it and go run around in it. And so that's a picture of a tunnel in the ice. And then this is the process that's going on. It's just like a tunnel, water tower, and it feeds water here. But I still, after showing this, I had people saying, how can water run uphill? And so I need some volunteers to help me. And we have an experiment to show you. And I hope it works. I need one other person. Okay. And you go this side. Oh, it's got to be this way. This side. And you can hold this side. And you get to hold the water here. Catch the here. And I had brought some red-colored water, but sad to say it leaked in my car. And then I forget, I don't know who, somebody was very kind to us here, and she said, why don't you use Windex? And I said, that's a great idea, because it's blue also. Now the big question is, will the water run uphill? This is where your tunnel valley is going to form, right underneath here. Will the water run uphill? You ready? You did it? Well, everybody wants to, usually everybody says, do it again. They don't trust one experiment. Okay, so it worked. So if we can lift this up so we don't, there we go. Thank you very much. Oh, okay. Yeah.
What is the speed of that water?
Oh, it's going to be fast. It's going to be miles an hour. Yeah. It has to be that fast. Can you put it in there? Thank you. It has to be that fast in order to carry the size of the sediments that are coming up. It's bringing out couples. And so it's going to be moving quite fast. All right? So, did that convince you that water can run uphill? Well, Windex, maybe only Windex. Okay, characteristics of tunnel valleys. We've seen them. They're frequently sinuous and form anastomosing patterns. I don't know if people are in biology or in medicine, they say, oh, I know anastomosing. I didn't know it existed anywhere else but biology, but it does. Sorry? Well, anastomosing was a pattern we saw where it goes like this. And interconnected, and water travels along, decides to go a different path. Okay? And it may terminate in outwash fans at ice marginal positions. You saw that, right? We saw that to the fan.
I was told by a geologist once that in Fort Jefferson Harbor, if you look on either side, there are hills on either side of Fort Jefferson Harbor, and that they were formed by the pressure of the water outwashing from the glacier. Like if you put a garden hose in the sand, it would push up the material.
Oh, no, the stuff on either side has not been pushed there. It's been eroded. The surface was a flat across, and then when the tunnel valley formed, it eroded it off. And on the Belterre side, that is actually also a separate moraine formed between two ice streams. And so they go uphill and downhill. Tunnel valleys can go uphill. Everybody can agree that now?
Yep.
And so the next thing I want to just show you the pictures of it then to remind you. Here's the anastomosing pattern, right? People see it? Oh, quite often do that, push the wrong button. How to make a kettle. Most people have a misconception about how kettles form. Most people have thought about it and all, but the way they think about it, this big chunk of ice sits on the surface. The weight of the kettle depresses the surface below it, and then when it melts, it fills with water from the melting ice. And that's not true. Okay, so here is how you do it. You get a chunk of ice, and it's buried in the sediment. In some cases, it's been deposited on the surface, and then the outwash sediments just come around and bury it. And so it gets buried, and then when the ice melts, you get a depression. Then, is there water in every kettle making a kettle lake? No. On Long Island, there are hundreds of kettles. Right on our campus at Stony Brook, we must have 10 or 15 kettles, and they're all dry. And the way to get water in it is that if the groundwater is below, this is the groundwater table, is below the bottom of the kettle, there's no water in it. It's dry. It may have water in the spring or when it's been heavy rain, and then that water just drains away. It's the same thing on the ice. When the ice melts, it just can drain below, or it just evaporates. Because it doesn't take very long. And so in order to get water in a kettle, you raise the top water table. And then you'll get a nice kettle lake or a kettle pond. So that's the key thing there. Is that only if the water table intersects it do you get a kettle lake. So, history of Long Island Sound Basin. I think some of you are interested because there it is, right? Okay, 30,000 to 26,000 years ago, this is what it looked like. Here's Connecticut, and here would have been the future Long Island, and you can see there would have been lakes in there. It would have been somewhat of a high area, but probably not high enough. Well, that's enough, somewhat high area. And then the glacier came down. You see all the waters coming off. Here it's forming Ronkonkoma moraine. And the sitting there over the thing, the channel. Then 20,000 years ago, the glacier retreated. It formed then what's called Lake Connecticut. It's a glacial lake. A glacier because it's a part of a glacier. You can see it's dammed by the Harbor Hill Moraine, and it's a nice big freshwater lake. Then 15,500 years ago, it drained right through here. That's called the race, if people are familiar with it, in the sound. And that's where the water drained out. And then 9,000 years ago, the seawater was continually slowly coming into the sound. Then 9,000 years ago, it finally covered the bottom of the sound. And since then, it's been rising continuously till present day and into the future. So let's go to the climate history. This is something that usually isn't thought about in terms of glacial things, but it's kind of interesting. Here is a map, a graph showing temperatures. This is in centigrade, so this is minus 12, minus 10, minus 8. This is from 20,000 to 18,000 years ago, and the temperature here then was in Fahrenheit. Mean annual temperature was 15 degrees Fahrenheit. The mean annual temperature right now on Long Island is 54 degrees Fahrenheit. Right now, our mean winter temperature is 33 degrees Fahrenheit. Can you picture now a temperature system like that, where half the time the temperature is above 15 and half the time it's below 15? And that would be chilly, right? And so it's quite a different history there. And this is a picture showing how you can use ice cores. They take ice cores and they can actually check up on the history from Greenland, because for the North Atlantic areas, this gives us a good hint what went on. And here's just a picture that just shows then from 18 to 15,000, it was really quite cold. This is temperature here. This is temperature, this is snow accumulation. So temperature stayed pretty cold till here, and then we'll start warming up around 15,000. We'll talk about this other part here later, but the key thing is that when the glacier left, it was not leaving because it was warmer. It did not get warmer. It left when the temperature here was very cold, and it stayed cold as the glacier retreated. So it wasn't retreating because of warming. It was retreating probably because less snow fell on the area on the glacier during the winter, and then melted in the summer. So what was the weather like 20,000 years ago? Mean annual temperature was 15. Ground was permanently frozen to hundreds of feet below the surface. In the summer, the upper few feet would thaw. And the area was called the desert tundra. Very little rain or snow. You figure about 8 to 10 inches equivalent of precipitation a year. And this would be, picture this Long Island. That could be the Ronkonkoma Harbor Hill Moraine, okay? Not really, but you can see that's what it would look like. And this would look like, of course, in the winter. And then a nice picture of the tundra in the autumn.
We have some of that somewhere now, don't we?
Sorry? Yes, these are pictures from up in the tundra in North America.
But what is the mechanism that makes the temperature change so widely, actually in a long time?
Well, in this case, it's really cold when you're right in front of the glacier, because the glacier has, the top of the glacier is very cold, and all those cold winds come off the glacier. So it's actually self-supporting to get it that cold. And you get huge winds. If you're familiar, you may have heard of katabatic winds, or föhn, if you're familiar in Switzerland, or in what do they call the winds in California? The winds come down the hill, and then they can be very steep. They can be very cold to start with, and still cold when they get to the surface. So that'll keep it cold. Just a cold glacier there.
But what is the basic reason why the temperature in this part of the earth around the world is changing? What is really
Well,
the mechanism?
the mechanism in the glacial period is thought to be the sunlight, how much sunlight is affecting the North Atlantic, because the thinking is that that's controlling how much, how the currents flow in the North Atlantic.
But why is it different sunlight then than some other time? Why?
It's always changing. Right now, we're at a point where we're having a very low in our sunlight, and people would suggest that if it weren't for global warming, we'd be going into the glacial age right now, and it's expected. The period of interglacial periods are 10 to 15,000 years ago, and that's essentially the time when we came into the interglacial.
Because the sun puts out more or less light?
No, it's just the orientation of just the orientation.
So the tilt of the earth, and that's all I can think of.
Tilt of the earth, the distance from the sun.
Oh, the distance.
Yeah, we change. There's an elliptical pattern around the,
Okay.
and so it changes ellipticity. It's sometimes circular, sometimes more elliptical, and then it also the change in the tilt.
So it's the tilt of the orbit, you mean,
Yeah.
of the Earth. The tilt of the plane of the orbit of the...
No, that's an ecliptic. That stays pretty constant.
Oh,
It's the tilt of the Earth's rotation,
oh.
and that changes.
So you're saying global warming is helping us?
Well, that's up to each individual. I would say that for some people it'll help them, but most people it will not. Because, especially, well, this is my opinion anyway, it's mostly going to hurt the poorest people.
It's a matter of centuries. The global warming, the tons of things is longer, millennia.
Yes, yeah, in glacial things, that's millennia. What's happening now is years, tens of years, right? And these are some of the animals that were roaming here. Woolly mammoths, saber-toothed tigers, cats, saber-toothed cats, they're going to call now. Muskox eating the shrub willow. Caribou eating caribou lichen. And here's some caribou lichen. And if you go to dwarf pine plains, you'll actually see caribou lichen. Here they call it reindeer lichen, but it's still growing on Long Island. So, about 15,000 years ago, it began to warm. And we went from a spruce to a spruce forest on permafrost. And this would be an area in Alaska, the spruce forest on a permafrost, so it started looking like this. A little bit different, nicer. And then in Siberia, we might have had that here too, they have what's called the drunken forest. And so you can picture if it's permafrost and it's only, it's thawed in the summer until about that depth, and it's going to be filled with water. So if you're a tree and you're getting pretty tall and something sort of pushes you, you're going to tilt over, right? And so you get what's called drunken forest. And at 15,000, you get the mastodons coming in. The mastodons are more or less replacing the mammoths, because mammoths are grazing animals. They graze on the sedges and grasses. They prefer that. And the mastodons are browsing animals. They like to eat on the trees. And there's a difference between a mammoth and a mastodon. There is some difference.
And what's the effect of the polluting of the atmosphere on that?
On which?
I mean, on the changement, what's the effect of the changing of
Right now?
the pollution in the atmosphere?
Well, right now, the
Yeah,
concern are greenhouse gases.
Yes, yes.
And the greenhouse gases, they've known since essentially the middle to late 1800s, that the CO2 and methane, when you shine infrared light on it, it gets absorbed. It doesn't go through. Water is the same. Water, it gets absorbed absorbs infrared. So what's happening now is you increase the CO2, quite a bit of the infrared would be escaping from the Earth, but the CO2 in the atmosphere is absorbing that infrared, so it isn't escaping. So it's a case of just catching it and keeping the heat here.
So what is that, the effect of the changement of, you know, say, when the glaciers change so much, there is any effect from the pollution of the atmosphere?
I don't understand the question.
I mean, now there is a big question about if we are polluting the atmosphere.
Yes, we are.
What is the effect of that on the mechanisms?
Well, it's a separate mechanism from the effect of the orbits and the changes of the tilt. This is an additional sort of thing.
This is an additional.
Yeah. Okay, the Younger Dryas. About 20,000 calendar years, glaciers left Long Island. It was cold till about 15,000 years when it began to warm more rapidly. And some people think we were coming out of the glacial period, going into interglacial period. And then about 12,900 calendar years ago, it suddenly turned cold again, really cold. And the cold lasted till about 11,500 years ago when it warmed. And this is just a picture again. And you can see, here's 18,000, starts to warm a little bit then, and then at 15, starts to get really warm, and then at 12,900, the temperature just slipped. And when they look at this data from the ice cores, they say they can't, it went as fast as they could measure it in the ice cores. That they can measure years on that. Yes?
Why did it get so cold all of a sudden?
Well, that's a question people are concerned about. Sorry?
They don't know why.
Well, the best hypothesis, or the most, not the best, the most favored hypothesis is that something dumped a lot of fresh water into the North Atlantic that stopped the Gulf current and the other warm currents that are going up into the North Atlantic. And when they shut it off, then there's no longer any heat brought into the north. And it stops it because the current goes up warm, it cools off, and gets denser, and it sinks. And without the sinking, you can't have the circulation. And so if you put fresh water in it, the water that was originally going to be higher in density will no longer be higher in density, and it stays at the surface. It stops the current. And you stop the current, the whole North Atlantic area will get cold. And here it says it's going to be looks very severe. That's probably the most accepted hypothesis.
When were people able to walk from Siberia into Alaska?
They started around 14,000.
And that's when sea level...
Sea level was lower then, and sea level was pretty low even then, now. And it went down really fast.
10 degrees Celsius.
Yeah.
10 degrees,
Yeah. And so then here you can see the ice core got warm, and then right at 12,900 it got really cold, stayed cold, and then warmed up, and it cooled off as fast as they could measure it, counting years. And they figured it could be as few as 1 or 2 years it could have dropped. And then of course it warmed up. Another one occurred here, a similar event, where it was much less change in temperature. But even that had severe effects on humans, because by this time you're starting to get, this is 8,000 years ago. You were in agriculture and things like that by then. So there were serious problems just from that change. And then it was pretty warm through this period, and then about 4,000 years ago it started cooling again. And then you can see this is the little ice age. That's not much change at all, but the effects in the North Atlantic area were severe. You probably have heard about during the little ice age, there were huge plagues in Europe where 30% of the population were killed off. They think it's because they malnourished and even though the fleas brought in the bubonic plague, because probably people couldn't stand it because we would perish. And I went in Russia to this one farmhouse built in the middle in this period, the Ice Age, and the doors were this high. And so I said, well, I asked the guy there, I said, well, were people you wanted to save the lumber so much they made the building shorter? He said, no, people were shorter then. And because it was ice, it was cold, you couldn't, or because the temperature was cold, you couldn't grow crops.
Those temperatures negative over there?
Yeah, these are temperatures for Greenland. So you don't think about converting them to our temperature.
Minus 30 Celsius, that's very low.
Yes. Yes. It's warmer now, but still, yeah, that's today. Yes.
It's amazing.
But it's on the top of the glacier. Okay. So let's go on. 12,900 years ago, Dryas octopetala appears. And this was a very surprise to people because they're looking at bogs. And then Dryas octopetala is a beautiful flower that grows only under the coldest conditions. And they looked at the core, and they saw the lower cores. They had Dryas in it, and then it disappears, got warmer with pollen, and then all of a sudden Dryas octopetala came again. So they said, something's funny there. And so they called it the younger Dryas, because there was a less important period where they had Dryas coming up earlier. That was the older Dryas. So that was a hint that something was going on. And then, 12,900 years ago, the Clovis culture disappeared. And some of you probably know about it. They were the hunters of the big animals, megadon. And that's because some people think because the megafauna went extinct. And that's a big question. Why would they go extinct? Some people said, well, they couldn't take the cold. Well, they've been living in cold conditions all their life, so it's not clear exactly why they died. And then list-like sediments deposited on Long Island. These are silt sediments. That's why I'm bringing it up. And so then, this is octopetala.
I see only 7.
Huh? 1, 2, 3, 4, 5, 6.
Not 8.
Well, they should have 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6.
7.
Oh, it depends on which direction. Well, I'll accept the fact that most of them have 8. Okay. Then these are the Clovis periods from the Clovis culture. Right? The Clovis people are in North America. They were first identified in I think in Arizona, wherever Clovis is, Arizona, I think, somewhere in there. But they were very abundant. I don't know if abundant's the right word for people. In the north, in the east, there were just lots of them in the east, more so than in the west. And that's because the conditions were probably more favorable here. And you can see. Do you think they were hunting rabbits with these? Okay, so then it just got warm, and we did some work on Lewis. Lewis is a wind-blown silt. I mentioned it earlier. I hope I'm not too late now.
It's okay.
Okay, and we looked at it at Stony Brook University because we were interested in when did the Lewis form? Because we're interested just when were the winds blowing all this silt around, because Lewis is a wind-blown silt. And so this is on campus, and we have a 3-foot section of Lewis. It's sitting on top of a little bit of sand and till. This is a typical sort of North Shore picture. Lewis and till, and sometimes sand, sometimes no sand. And Vesta Kundich got an age of 12.3 thousand years. That surprised us. We expected it to be right after the glacier left, 12,000, about 18,000. No, it was 12.3. That was weird. Why would we get an age like that? And then Wildwood State Park, she also did a core in Wildwood and got a deeper core here than the 3-foot one. And she did it, and while she was working on it, she was not really annoyed, but a little annoyed, because her hands kept getting black while she was working on it. And then she couldn't figure out, and then she said, oh, I better go look, see what's causing my hands to get black. And she looked and she said, oh my God, there's charcoal in it. And then on the campus, we also found charcoal in it. And we didn't know why there should be charcoal. And then she dated it, and that came out 13,800 plus or minus 1,000. 13,400 plus or minus 1,300. This one's 7,700. You can see now these are consistent with them being of younger Dryas age. So we're thinking now that something really serious happened at 12,900, because these are within that uncertainty. And now a lot of studies have been done on that period, and it seemed like there were huge fires all over. And we don't know what caused the fires. And the fires had to burn long enough so that the area would become barren, and then you could get the winds to blow the dust around. And so that's what's probably happening. And here we got a carbon-14 age, 11,200, which is at the end of the younger Dryas, which is consistent. So this is consistent with the younger Dryas age. This is probably the 8.2 event I mentioned earlier. And so this might be what it was like at that time. So for whatever reason, we got huge fires. And some people have suggested that huge fires were because a comet broke up and dropped all sorts of little pieces, large enough so that they could cause fires in the area and kill off things. And they also would suggest this is why we got rid of the Clovis people and the culture, not the people necessarily, and the megafauna. That's at least one hypothesis for the end of it. So it's a very interesting period, and it's one I've been working on, and I don't know that we'll figure it out very quickly. Okay, so 11,500 years ago, younger Dryas ended, climate warmed rapidly, end of the last glacial period. So, just to review, glacial climate, geologic climate history of Long Island. Glaciers during last glacial maximum here were 20 to 25,000 years ago. Most of the surface features on Long Island were created between then and now. And you get bush moraines, tunnel valleys, kettle holes, was, and then the younger Dryas event. And then the climate has changed from desert tundra to temperate forest, which we're in now. And the end, and I don't know if you're familiar with that, is that's where we're sitting right now. Well, look at it. Yes. But a way to recognize a tunnel valley is where you're traveling on it. You look to your right. Is there a wall? You look to your left. No, I shouldn't call it a wall. At first, just see a rise in the topography. Look to the left, see a rise in topography. And are you going on a gradient?
Yes, that's what we do.
And if you are, that may not always be a tunnel valley, but on the North Shore, that's a very common way of saying tunnel valley. And usually when I give talks, afterwards when people say, oh, I live in a tunnel valley, it's the first time I've given a talk and said, we are in a tunnel valley.
Our early pictures,
Huh?
the early pictures of the village.
Yes.
Our earliest pictures, we had giant what do you call it? Tunnels. We had giant going down to the water. They filled
Like a gully.
gullies. Yeah, we had big
Or
gullies.
this
They
is
filled
filled,
them
this
all
is not
in.
filled right here then.
Yeah. Yeah.
Okay.
We had big ones. They filled in. We have some
Yeah.
pictures of it. Yeah.
Okay.
That's great.
Professor,
Yes?
I'm under the understanding that the reason that we don't have harbors further east than Port Jefferson is because of the angle of the island and that the wave action and erosion from the Atlantic has eroded them all. Is that?
Yes, that's a pretty good model.
Okay.
I don't know if I can get back to a picture of it. Maybe I can't get to it fast enough. You're patient?
We're patient.
There, no, that's not right. I had one picture of like Long Island here somewhere.
Yes.
There. Yes. You can picture, this is the Harbor Hill Moraine. It probably continued like this, right? And so the erosion of the North Shore is probably mostly from nor'easters. Because when a nor'easter comes in, you get a big nor'easter, it's sitting off here somewhere, further northeast. And it has northeast winds coming in. And if it stalls, it quite often stalls. Remember it was 1995, we had the big one? It stalled, it sit there, and then because Long Island has a big opening on the east side, and just the East River on the west side, the water gets blown in from the northeaster, and then at high tide the water comes in with the wind, and then the water rises, and then when you go to a low tide, the water doesn't go out, it's still being blown in. So the next high tide, if it lasts long enough for two high tides, the next high tide comes in and more water comes in. And so that means that during those kind of events, you get a lot of erosion, especially on the eastern part of Long Island. And it's pretty much has eliminated this sort of material. You can picture that was probably going across like that.
Is there any evidence that there were harbors further east that's identifiable?
I don't think so. Yeah. And you can see these harbors are all tunnel valleys. They're formed by tunnel valleys. Yeah. Well, I'll give somebody else a chance now. Okay.
So is the bluff which we have today, is that the same as the Harbor Hill Moraine, or is that?
I'm sorry?
The coastline here, which is this.
This here?
Yeah,
we're on the Harbor Hill Moraine right here.
That is okay.
Yes.
So, but further west of here, there is still a bluff, right?
That's Harbor Hill Moraine.
But in Harbor Hill Moraine is further inland. So
Yes.
what caused the bluff there?
This?
No, further to the coastline.
Oh,
That's still pretty steep there, right?
yes. That's just the moraine. The moraine is extending. This is the front of the moraine, but the moraine really is going much further back. And that's why you get these tunnel valleys coming in and forming the harbors. There are a lot of them.
Well, then that's the south of the front. Hard to read question.
This, somebody might be explaining it, but I've been really emphasizing this part of Long Island. That's because it's easier. I'm there, and there's still a lot to do. Okay.
Well, this is also a political question. What do you think about the impact on the atmosphere by human activities now?
Well, I'm not a climate scientist, but from what I read, when they do models, they can put in the parameters. They can usually predict pre-existing effects of climate by their models, and they say then that they're fairly confident that they can also then predict the future.
So, I mean, but what's the result? Is a big impact or not?
On humans?
Yes, on the climate and all this phenomena.
Well, you're going to see the changes in terms of what's happened in the past aren't very large. But when that was happening in the past, say they estimate on Earth 20,000 years ago there were 3 million people on the whole Earth. 3 million people. By 10,000 years ago, they figured there was probably around 5 million people. 3 million people is the population of Suffolk and Nassau County. 5 million needs to do are Queens and Brooklyn. That was the population of the whole world development, if something changed, they would just move. Is that right? We can't move. We can't move. We got 97 billion people. And that's what's happening now. We're getting people who are forced to migrate. And people, places where they want to migrate, people don't want them. That's going to be the most, I think, to me, the most serious problem. We can't move.
The Sun Valley